Chris ELIASMITH, who is a co-CEO and president of Applied Brain Research, a leading neuromorphic company. He has won the prestigious 2015 NSERC Polanyi Award for his research. Chris has published 2 books, over 120 journal articles and patents, and holds Canada Research Chair in Theoretical Neuroscience. He is also currently the Director of Center of Theoretical Neuroscience at the University of Waterloo. Chris?
Thank you very much for that introduction, Joseph. And I guess I should note, given that introduction, that I am here as a representative of Applied Brain Research, which I'm also the co-CEO of. We're about a 20-ish person startup out of Waterloo, and I've spun out of my lab. So I wanted to talk today about something that we call mangocloud. And you can sort of think of this as a talk which is essentially announcing the release of mangocloud and inviting, as I will at the end, people to come and try it out. And really, this is unsurprisingly, given the tinyML context, a hardware-aware training platform for letting you not only bring your data to a deep learning optimization platform, but getting that data all the way onto a specific piece of hardware and being able to gather metrics on that hardware so you know exactly what you'll get when you go to deployment. So I'm not going to spend a lot of time on this because everyone already knows that Edge AI is a huge opportunity. Here's yet another chart saying that there's unprecedented growth. Yes, as I was mentioning, in order to sort of take advantage of what everyone already thinks is a great opportunity for Edge AI, there's a lot of significant challenges. And of course, many of these are familiar. So, not only do you need to understand artificial intelligence and all the many techniques that are there, but you also have to have good software development practices. You need to understand the hardware in order to map your model efficiently onto that piece of hardware. And you kind of have to bring all of this together in some consistent way. And on top of that, if we look at the current available hardware platforms, there's a huge number of them, right? So there's a significant amount of fragmentation, meaning that we have no general software tools for targeting, the 1500 ARM variants and the many other Edge AI pieces of hardware that are being announced. And, this stable of beasts is growing daily. So why is that a challenge? Because it means if I'm trying to make a decision about what the right hardware is for my application, I have to set up different development environments for each of those, which is often complicated. And there's all kinds of subtleties. As you know, this can take several days per environment. You then have to understand how to optimize for each of those different targets, which can be different depending on assumptions about the precision that's used, the way the memory is structured, and so on and so forth. This landscape is also constantly changing. So if a new variant comes on, I have to go through that entire process again. And it makes it very difficult to compare across options, right? So how are we going to handle this problem? So we at ABR are basically trying to build a development platform which is targeted all the way from the data to specific hardware where you can get metrics without ever having to build those environments yourself, i.e. you can do it all in the cloud. So you essentially upload your data set, you specify the model that you would like to apply to that data set. We have all kinds of optimization techniques of the variety that every tool of this type has, where you can be crushing everything down. We then deploy it onto a specific piece of hardware, which is running in the cloud. So you know that it's running on that hardware. You can communicate directly to that hardware. You can get all of the metrics you need, including power usage, memory, latency, accuracy, and so on that specific piece of hardware. And then you can make decisions by doing the same process across a couple of different pieces of hardware and comparing them in a very consistent way. And once you want to actually deploy locally, you can essentially download the relevant binary and put it onto your board. So in order to do this, we're essentially extending the ecosystem that we already have, which we call Mango. That ecosystem is really focused on distinguishing model specification and sort of optimization on standard hardware. So breaking that out from actually deploying it on all kinds of unique hardware, including neuromorphic hardware, which we've looked at in the past. But mangocloud is really focused on commercially available hardware, various MCUs, and so on. So really, I think the way of understanding what we're trying to accomplish here is, of course, we've got a lot of the kinds of features and so on that you see across the board when you have any cloud-based AI service. But in this instance, we have basically had to build a cloud service where you can actually put each of the kinds of hardware you want to target in the cloud, right? So that takes it out of the hands of the person that wants to do the comparison. So you can make a data-driven decision about what would be the right hardware for your particular application. And once you've made that decision, then you can, set up all the development tools, et cetera, that you think are relevant for you, and off you go. But it really helps bridge that gap from I have a model and I know I want it on hardware and I know I want it compressed to what is the right actual piece of hardware for me. Okay, so that's the sort of rough high-level description of what you get when you come to mangocloud. But we are a little bit more excited than just sort of offering something which we think kind of many software development teams could do. In particular, we have what we like to sometimes call our special sauce, which you also get when you come to the mangocloud. And this is a new kind of recurrent neural network. This recurrent neural network we call the Legendre Memory Unit. We published it about a year ago at NeurIPS. And it's very unique in the sense that it is optimal, right? So very seldom do you actually see neural networks where you can make optimality claims. Here we can claim and demonstrate that it's provably optimal at compressing information over time, right? So really our focus for the entire pipeline is making sure that temporal data is something that you will do a very good job of leveraging. And I think when you go to the edge, this is a very natural thing to do because a lot of the time the information you're getting is structured over time. What this lets us do is, basically get incredibly good performance results like the one that I'm showing with this graph, where we're comparing that LMU to an LSTM. So the LMU here has 80 times fewer parameters, but nevertheless, it is decreasing the mean squared error by 10 to the 6, so it's 1,000,000 times more accurate. And at the same time, it's remembering 10,000 times more data. So it has 10,000 times more time steps. And you might ask, well, how does that work? And the answer is basically that, the LMU is a dynamical system, and that's why we can make these optimality claims about it, which in the limit of having continuous information is going to be doing extremely well. And so the way that we're increasing the number of time steps is by essentially taking a continuous white noise signal, compressing it over some length, over some window, and we can sample that window more and more finely, which is increasing the number of data points. And for an LSTM, more data points basically means it's trying to figure out at every moment in time how to store each of them. But for the LMU, it sort of leverages this optimization in order to compress that information optimally, right? So you can actually get a better reproduction of the original input signal after you put it through the LMU than you can with other techniques, even for extremely long time series. So what does this mean when we turn to the standard deep learning benchmarks? So this is one example. This is kind of the standard. If you have a new RNN, compare it on TSMNIST, and that's what we're doing here. So from the original paper, you can see at the bottom in bold there, the LMU is outperforming all of the other RNNs proposed to date. As well, it's using 60% fewer parameters than all of those other techniques. More recently, we pushed this even farther, and we're up now over 98% accuracy on a LMU architecture, which is slightly simplified. And of course, we've applied this to many different application areas, cybersecurity, natural language processing, and we are beating transformers as well as LSTMs on those kinds of benchmarks. So it's very powerful and quite general, and we're continuing to push it. For the mangocloud in particular, we're really focusing on speech, right? And in particular, because we're looking at tinyML keyword spotting. So what we're doing with this graph is demonstrating how the LMU compares to state-of-the-art results published from a number of places. So Google had this fantastic paper in July where they surveyed all of the people doing keyword spotting on the speech commands v2 data set, and they went and additionally optimized those models for streaming, i.e. the kind of thing you could actually deploy. And in the top left corner, you can see the results that they reported there. And the LMU, as you can see, is hitting the maximum accuracy that they reported, but is also smaller. So smaller models are going to the right in this graph. And that's a log scale, so it is quite significantly smaller. And we can push that model smaller and smaller. And as we do, you can see this sort of Pareto optimal front showing up where it is still hitting sort of the best accuracies reported for those sizes of models across a really wide range. So this lets us make claims like the one that we have on here, which is that the LMU gives us the world's most power efficient streaming keyword spotting models because they're the smallest. And putting this all the way onto hardware, here we're comparing to ARM's results. So matching accuracy, but demonstrating a 10 times faster inference speed, and which means that you can do 9 other things, or you can just save that power if you want. But this is kind of just one, like all the way down to the hardware example of improving over current results on the M7. So to give you a quick run through the mangocloud interface, it's going to look pretty familiar. So you come to the mangocloud and you can start a new project. When you start a new project, you can specify which data set you want to use. So this can be one of the standard ones already there, or bring your own. And you can specify how you want it to be changed, what kind of validation, test, and so on splits that you want, if you want additional noise, et cetera, et cetera. You then configure your model. So this is an example of an LMU. You can then specify parameters of the model. And once you have picked those parameters plus a piece of hardware, so you always need to specify what hardware you're targeting, you hit optimize and it goes away and uses our various techniques for compressing that model onto the hardware in ways where we take knowledge of that specific piece of hardware and incorporate that into the optimization. You can then see the results. So all the standard results you might be interested in, including things like power and accuracy, which are run right on the hardware, right? As well as latency. So you can get all of the things that would matter for deployment in the real world are available through this cloud interface. And you can also interact with it to an extent. So you could record new keywords or sort of put in additional tests and see how it performs under those examples that are kind of live. Right, so kind of completes my description of this new mangocloud that we are just completing. So we have literally, just came from a meeting today where we are putting the final touches on the full pipeline and interface. And we are now interviewing to select and work with specific alpha testers. We have a couple of people on board already, but if you are interested and it sounds like the kind of thing that you might be able to use, please contact us either at the address here or feel free to contact me. Thank you.
Thank you, Chris. So we have a question. What type of parameters define the hardware? And did you analyze all of the hardware devices you stated to give a better neural network for each?
Yeah, so excellent question. So no, we definitely have not built backends. So we refer to the hardware targets as backends. We have not built backends for all of the targets that I listed. We have selected several. And one of the things that we're doing with our alpha testers, of course, is making sure that we have optimized for the hardware they're interested in, or we can add. So we basically have a process where we can very quickly add particular hardware targets that people are interested in. We've picked the ones that we've done to this point. We've picked from a broad array of kinds of hardware. So some are like microcontrollers, others are much more like sort of optimized for dense matrix multiplication. So we are very familiar with the optimizations for each of those, but yeah, they're not all currently available. So if you're interested in a particular hardware target, please talk to us. I think the first part of that question was what parameters are we using to characterize the hardware? I think maybe I've kind of answered that question as well. Is that basically we are targeting specific chipsets as well as specific boards, right? So as many of you know, when you're doing development on different boards, you have different kinds of constraints, and you really want to take that into account as well. So again, this is something that for our particular testers, we make sure that we have exactly the hardware that they need.
Okay, great, thank you.
I'd like to acknowledge our sponsors. First, it's ARM that develops software and hardware for tinyML. Qualcomm, Samsung. These three are the executive sponsors. And then followed by platinum sponsors. ETA Compute, Lattice Semiconductors, and the gold sponsors are BrainChip Corporation, Cisco, DSP Group, H-Impulse, EMSA Visual Sense, General Matter Labs, Greenwaves Technologies, Hymex, Imagimob, Legendre AI, Maxim integrated, Hixo, Reality AI, SenseML, Silicon Labs, Sentient, and Google TensorFlow. XMOS, and the silver sponsors are H-Cortex, HOTS, and SynSense. Again, we are very grateful for their continued support, and this is a great testimony that the foundation and this community is really of huge interest for the companies and for the whole world.